Okay, we are going to be looking at using our reaction quotient today to determine equilibrium concentrations. Now, this is part one of three different lessons that you're going to look at where you are going to be calculating equilibrium concentrations. Now, these problems that we're going to be looking at kind of takes a few of the lessons that we've done recently and put them all together. And so the best way to learn how to solve these problems is to do an example. Part of this lesson is already on the page, and part of it I'm going to write in as we go. So it's probably in your best interest to just hit pause and copy when you see something new, and then listen and fill in what you see me adding in. Okay, we're going to look at an example today. We have a reaction of carbon monoxide gas, and water, making carbon dioxide gas and hydrogen gas. Now, we want to know that if we have initial concentrations of each entity is 1.0 mole per liter. Oh, I'm missing part of my problem here. And if I'm just going to write. All right, so sorry, concentration of each entity. So that means everything in the system is 1.0 mole per liter, and the K equilibrium is 5.10. We want to know what the equilibrium concentrations of each entity will be. So before we can figure out the concentrations, calculate for concentrations, and do an ice table, we have to know the direction the system needs to shift in order to reach equilibrium. So to do that, you're going to use a Q. All right. So your first step is to use a Q. You're going to calculate and use Q to determine reaction shift. Now, for good communication, you're going to write out exactly what you see here. Knowing that we calculate Q exactly the same way we calculate K equilibrium. The only difference is Q is not using concentrations at equilibrium. Q is using the concentrations that we currently have. So we write out what we see, our formula, products, concentration of products over concentration of reactants. We sub in the values. They are all subbed in at 1.0 mole per liter. If we do this math, we see that Q equals 1.0. Now, that's important for us because we have to use Q to determine direction that we are going to shift. So our Q is equaling 1.0, and our K equilibrium up here is 5.10. So we know from our previous lesson that we have to compare our Q and our K equilibrium. So 1.0 is less than K equilibrium. So we're going to write, since Q is less than K equilibrium, therefore, we know that when Q is smaller than K equilibrium, we're going to get a forward reaction. So the products are going to be favored, and we're going to shift right. This is really important because this is going to tell us what the change will be in our ice table. So now we know direction. Our next step is to set up an ice table. So I have a skeleton ice table here, right here. We know, actually, I'm going to scroll back up, because we know from our initial problem that the initial concentration of everything is 1.0 mole per liter. So I'm going to bring that down to our ice table, and I'm going to pop that in. Now, I'm not going to write my units in after every number in my ice table because I have put it beside the I, the C, and the E. I'm going to hit pause. All right, so we have our initial concentrations in for everything, and now we have to do change. We know they're all going to be an X. of some form. X, 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 X. So a quick look, there's no coefficients beside a 1 for us to carry down, so we don't have to do that. But we know that one side of our reaction is favored, and so that means that it is going to gain concentration, while the other side of our reaction is not going to increase in concentration. It's going to decrease in concentration. So we calculated Q to tell us that direction our equilibrium is going to shift. And our equilibrium said it is favoring our products. So what that means is we are going to gain products. So X for our products is positive. Okay, so if you want, make yourself that little note that the positive, the products are gaining X, so they get a positive because our Q calculation told us our forward reaction is favored and we're going to shift right and make products. So in order to reach equilibrium, the change in concentration to our reactant is going to go down because we are shifting to favor product formation. So therefore, these guys are going to be a negative X. And if you want, you can make yourself a little note for that as well. All right, so negative because forward reaction is favored, so we're going to lose reactants. You know what to do now because the concentration at equilibrium is what we start with our change. So our carbon monoxide and our water are both 1.0. Oh, that looks bad. Subtract our X, and our products are going to be 1.0 plus our X. So now what we're going to do is something you are already familiar with. We're going to take these values that we've determined in an ICE table, and we're going to plug them in using an equilibrium expression and our K equilibrium value that we already know to calculate our X. So you're going to use our equilibrium expression to solve for X, and it looks like this. I'm going to fix the colors. All right, so we take our numbers from our ICE table, sub it into equilibrium expression with the K equilibrium value that we have, and then we arrange to solve for X. So if we look, we can take this and we can simplify it because what we have in our numerator is a number 1.0 plus X in a bracket times exactly the same thing. So what you really have is 1.0 plus X squared, and you have the same thing on the bottom right here. So we can simplify that. We can write it this way because now we can take the square root of this to simplify the equation to solve for X. So we can take our square root, and then we can actually get our square root, and we get something that looks like this. And then we have something that is fairly straightforward to solve. So I'm just going to show you the math because my stylus is not cooperating. So we have to take our lower bracket over here and we multiply it over across the equal sign. And then you have to use your simplifying rules or your expansion rules and multiply 2.258 times the 1.0 to get 2.258. And then 2.258 times negative X gives you negative 2.258X. And then on the other side, you just have 1.0 plus X. So you have to do some rearranging, and I have done all of the steps here to show you the rearranging. I have brought, it's actually easier if you keep X over here on the right. It stays positive. You deal with less negative numbers. So I would do that like you see what I've done here, and then flip it over at the end. Sorry, my children are loud. There's nothing I can do about it. Okay, so you can just kind of see through the math here. I arranged to put both x expressions over here, and I simplify it 3.258x. And I put the other two expressions on the left, simplify it here. And then I just did some division. And then I get x equals 0.386. Now, at the very end, after you solve for x, add your units. You do not have to carry units through this because it's messy. So just at the end, put the units in for x. So this is now looking like something you know how to do because you've been here before. You just have to use the x values to determine the concentrations at equilibrium. And for this example, it's really straightforward because your two reactants, carbon monoxide and water, were both 1.0 minus x. So you just solve in your x value, and you get them having a concentration of 0.614 mole per liter. And then you do the same thing for the products. You get carbon dioxide and hydrogen gas. They equal 1.0 plus x. I did this wrong. I didn't do the math wrong. I just wrote it wrong. I'm going to fix it. This is blue. This should be plus. Oh, it's a green plus. Whatever. All right. So the concentration for carbon dioxide and hydrogen gas is 1.38. That should be 6. Wow, I made 2 mistakes. My pen sucks, so it's not being overly nice to fix. Come on. All right, you're just going to fix it. On your notes, make sure you write this as 3.86 because our x is that. Okay, and then because you want good communication, you would finish this off with a therefore statement because that is important. All right, so I would suggest that you copy down the second example I have here and give it a try on your own. We have iodine and bromine react in a closed 2.0 liter container, 150 degrees Celsius to produce iodine monobromide, according to this equation. We have the equilibrium constant at this temperature is K equilibrium equals 1.2 times 10 to the 2. And we want to know what the concentration is at equilibrium for all entities if the container originally contains 4.00 moles of iodine and bromine. So what you have to do here to move forward is you actually have to calculate the concentration of iodine and bromine using the mole and volume information. You know that they both have 4.00 moles in 2 liters. So you can see that just a quick line, initial concentration of iodine equals initial concentration of bromine gas equals number of moles over volume equals 4.00 mole over 2 liter is 2 moles per liter. So what I'm going to suggest is you hit pause and you calculate your Q. So if you go to calculate your Q, you're going to have something set up that looks like this. You have only your initial concentrations of the iodine and the bromine are both 2 moles per liter, but you have 0 concentration of iodine bromide. So what that means is your Q is 0. Sorry, I just got interrupted. I don't even know what I was saying. All right, sorry. Um, the initial concentration of your products is 0. So what that means is mathematically, when you calculate out Q, it's going to be 0. Now, if you recognize that the products are, sorry, the concentration of the products is 0, then you know the equilibrium has to shift in the direction of the products. So instead of calculating out Q, you can say, since initial concentration of products equals 0 mole per liter, the reaction will shift towards products. So you can either mathematically show Q equals 0, and therefore Q is less than K equilibrium, because our K equilibrium is 1.2 times 10 to the 2. Or you can write our statement that we see right here instead. All right. So the Q is going to be less than K equilibrium, which means we're going to shift towards our products. Now, you still, if you calculate Q, you still need to make a statement that you are shifting towards products. Now, I don't have this whole problem written out right now, the rest of the solution. And my stylist is like not cooperating at all. So what you need to do now is you're going to do an ice table showing that the change is a negative X for your reactants and a positive X for your product. Take your concentrations at equilibrium from your ice table and sub them into the equilibrium expression, which you're going to do it properly by writing it out first, the formula first, and then subbing in the values. And if you sub in the values and simplify, it's going to look like this right here on my screen. And then once you solve for X, because you know K equilibrium, Evelyn, be quiet. Once you solve for X, be quiet. I'm almost done. Go away. Go. Sorry. So once you solve for X and you sub in to those values from your ice table, like you already know how to do, you should get IBR, concentration of iodine bromide, 3.38. Iodine gas and bromine gas are both 1.31. So try that, work through the process, and then see how well you do here. Okay, if you're stuck, pop into office hours. We'll do an example together.